All right, so now we're going to really dig into reaction rate. So we're going to really talk about some mathematical definitions and that there's a few different ways that can be measured, and so there's some terminology with it, depending on how we're talking about reaction rate or how we came about finding it. And so, as we talked about before, this is the speed of the reaction. This is how fast the reaction is going. So you can think of it like the speed of your car moving. You know, there's your position, that's like just our concentrations, and then there's the rate that they're changing. So your position is changing as you drive. That's your speed of your car. How fast is that happening? That's the speed of your car. There's our concentrations, and then they are changing as the reaction occurs. How fast are those changes occurring? That's our reaction rate. So this is like our speed of our reaction. That's why I draw that analogy. All right. And so we're going to consider it an extremely general reaction here. So we got A plus B makes C. So we got two reactants, one product. All right. And it's all one-to-one reaction. And this is how we write our rates is it's going to be equal to the change in our product over the change in time that it occurred. So if we went from 0 to 1 and it took 1 second to do that, our change in time would be 1, our change in concentration would be 1 molar or whatever. Well, then our rate is 1 molar per second. It's a weird unit, I know, but just hang in there. You know, it's change in concentration or change in time, so our units are always going to be something like molarity per second. Now here's the other thing. We have to have the same number for rate no matter what we're talking about. Maybe we can only determine what's happening to B. Well, what's going to happen to B? Is it forming? Well, no, it's a reactant. So it's getting used up, it's going away. Eventually it will zero out and our reaction will stop. So when we're dealing with something like a reactant, we have to put a negative sign in front. So this has a positive change. Both A and B here are going to have negative changes because they're getting used up. We start with a lot and we end up with none. We start with no products, we start with 0 C, we end up with a lot. That's how a reaction is supposed to work. And so when we're dealing with reactants, we have to multiply their change by -1, and that holds this equality. Now, no matter what species we're talking about, we get the same number for rate. We don't get a negative value here, we get a positive value across the board. So that's the first trick. And so these little square brackets mean concentration, and this is just, you know, compound C, whatever that is, whatever molecule that might be. So change in that concentration, delta means change, over change in time. So like I said, you see molarity, because concentration is usually measured in molarity, time is usually measured in seconds. So you get molarity per second as the unit there. All right, so this is our most simple example to start out. I'm going to keep it very general as we continue through here. So what if they aren't all one-to-one? What do you do? Well, how do we keep these numbers the same? So now we're going to have a situation where A plus B makes C and D. So we have two products, two reactants, and we have coefficients. So this little A here, it could be a 2 or a 3 or a 4. It's not 1. We'll say that. B, same deal, little c, the little d over here. So I use A moles of compound A plus B moles of compound B to make C moles of compound C and D moles of compound D. All right, so that's what our reaction is saying. We get two reactants, two products, and we don't use equal amounts of all of them. So when we have our rate, we need the same number across the board. So if I look at my product here, well, I know it's going to be a positive value. I'm creating a product, my change is going to be positive. I'm going from 0 to more than 0, so I'm increasing. And so it's still going to be, all right, I've got delta times concentration of C over delta T, but how can I normalize this? How can I make it so that it's going to be the same across the board? Well, I divide by the coefficient. So I go little c times delta T. And this is a big capital C up here. Make that very clear. All right, lowercase, uppercase. So you never guess what we do with D over here. Well, same deal. I just go change in concentration of capital D over lowercase d times change in time. And when I'm dealing with reactants, same trick as before, plus I bring in the negatives. All right, so this will be equal to change in concentration of A, negative change in concentration of A, excuse me, over lowercase a times delta T. And then we do the same trick with B, negative change in concentration of B over lowercase b delta T. All right, so reactants, we got to bring the negative sign in. And we were actually doing this trick before. Keep in mind, there's a 1, a 1, and a 1. Well, guess what we have here? We just didn't write them. So it's a universal rule. It's just that one time something, we're lazy. We don't write the 1. Because we have a 1 here, and here, and here. And so if these were all, if it was 1A plus 1B makes 1C plus 1D, well, then all these 1s would just be on the bottom. If it's 2s, we just do 2s across the board. But what it lets us do is it holds all these terms equal to that rate right there. Keeps that equality solid. That's what we're doing. So these are the tricks we have to do so that our rate doesn't depend on what species we're talking about. All right, so this is what we call our rate expression. So this is how we can express our rate in a universal way. So if I'm talking to someone across the country on the phone, I say the rate of my reaction was 0.45 molar per second. Doesn't matter if I was looking at the formation of C, the removal of B, the removal of A, or formation of D down here. Doesn't matter. We should be able to talk in the same language. We don't have to specify anything about how we're looking at it, just what we measured. And that lets us do this by doing these tricks right here. So that's the first thing. Now the next detail is, turns out we can play around with what delta T means, all right? And I'm gonna draw a graph on the left-hand side, so I'll erase and draw a graph here in a little bit. But we gotta monitor our changes in concentration over changes in time. That can be tricky. There's some experimental techniques we can do it. Normally when we have the lab for the class, you guys do an experiment where you can actually watch it occur with your eyes and you clock it with a timer. And you just go, oh, it took 45.37 seconds or something like that, and it changed color. That meant the reaction was done. So you do something like a color changing reaction. Or you can use a spectrometer, which you would do in the Beer's Law lab. You'd observe that technique, not necessarily for reaction rate, but just that compounds can absorb light. And so we can look at the difference in absorbance. That will correspond to concentration. We can figure out the differences and clock time again. All right. But essentially we just have to look for some way that we can figure out our change in concentration. There's some really dumb tricks, some really smart tricks. There's a lot of ways you can go about this. It just depends on the situation, depends on the reaction you're studying. Sometimes you're able to actually freeze a reaction and measure the solution. Different, by freeze I mean like stop, not solidify, but anyway, there's a lot of tricks, but that's not what's important right now. Just what we do with the data. Okay, that's where we're going. So this is something we do experimentally. How we analyze that data gives us 3 different types of rates. So we can do average reaction rate, and that's, we look at where we were, where we ended, and we just straight line between them. And that gives us a rate. That gives us a slope with everything, that's like delta T. Now if you're taking calculus, you'll understand what I'm saying. If not, don't freak out too much on the next one. But essentially, and I'm gonna draw a graph. I'll make it visual in a second. But instantaneous rate is, there's a tangent line. So we only look at one point. We find the rate of change at that one point, the speed at that one point in time. We're not averaging between 2 points. We're finding a tangent line at one point. And so like if this is like delta T up here, instantaneous is like dt. So if you take in calculus 1, you've done derivatives, that's where this comes from. And then there's initial reaction rate. And that's just our instantaneous rate at the very beginning, at t equals 0. What did it start at? Because that's going to be the fastest reaction rate we can observe. So that's what makes this one special. The reaction is going to start full speed. It's going to take off. And then it's going to start to slow down. Now I want you to think for a second why that might happen. This is going to really lean on the kinetic theory of chemical reactions. But as our reaction takes place, what's happening to our concentration of reactants? Well, there's a reason I put this negative sign in front. It's because they are dropping. The concentration is going down. If that concentration is going down, what's happening to our reaction rate? What's happening to the number of collisions we have between A and B? As there's less A and there's less B, are they colliding into each other more or less? Well, the answer is less. There's less molecules for them to bump into. You know, it's like trying to bump into somebody right now versus, I don't know, 3 months ago on a Tokyo subway. You couldn't help but collide with people on that Tokyo subway. Now, if you try to run it, they run away from you. You're like, ah, 6 feet, stay away. Like you can't get a good collision anymore, you know? So the reactions aren't happening. As it becomes less collisions, less reactions, less reactants, less collisions. So it's just kind of this string of logic, all right? And so that initial rate is when we have the highest concentration of A and B. We're gonna have the fastest rate we can observe. And so that's why it gets its own special category, because it really is just an instantaneous rate at a very specific situation, at a very specific point. And so it's our initial rate because it's the one we start with. So we take off, and then it's like we've run out of gas. We're slowing down. We're just riding it out. Gravity is slowly bringing us to a stop. That's what's going on. All right, so I promised you a graph. So let's make some space here. Let's talk about what these look like visually. Because calculus is not a prerequisite for this course. Don't freak out that I said that stuff. You're not going to be doing derivatives or anything like that. If you even know what that word means, don't freak out if you don't. But just understand the differences between these three. All right, and so if we have a graph here, we are going to plot something like concentration versus time. I'll write it all out. And, you know, so this could be molarity of seconds, something like that. And we've got a 0 here. We've got a 0 here. Whatever, that's 0, 0, okay? So this is when we start a reaction. This is if we have 0, concentration of 0. And so if we start out, actually let me get colors here. When we are forming our product, so we'll go with A plus B makes C. Keep it very simple. If we look at C, what's happening? Well, we have none. And it starts to form, and it starts to form slower and slower and slower and slower. So we get this curvature. All right, and so that's concentration of C right there. All right, and so let's look at just one of the reactants. We'll look at A. We'll go alphabetically here. Well, we're going to start with some amount, and it's going to do the opposite. It's going to drop, but it's going to start dropping slower and slower and slower. We're going to start getting more and more curvature. And so this is concentration of A. And so this is what happens to reactants. Their concentration goes down, product's concentration goes up. But the rates are changing, all right? And so depending on what we do, maybe we look at, you know, the concentration at this point and this point, all right? And the slope of this line equals our average rate between these two times. We're averaging out. The rate is not the same at any given point. Or we can look at the instantaneous rate. So a tangent line would just be a line that touches right at that point, all right? So this is a tangent line. So it only intersects our curve at one point, whereas our average rate is going to use a line that intersects at 2 points. Okay, and so that means that the slope of our tangent line is our instantaneous rate, okay? So if it just touches at 1 point, then it is an instantaneous point. Now if we only touch right here, right at t equals 0, well, guess what this is? Make some room here. It's our initial rate. Because it is an instantaneous rate, it is a tangent line that only touches right here. So that's what they look like on a graph. Now if we were to look at A, you know, if I do something like an average rate on A, bing, well, my average rate is going to be the negative of the slope. And that's going to get me, you know, data that matches. Because I don't want a negative value for rate. I don't want a negative formation of products. Think of rate as the speed that the products are forming. Well, the products are forming at the rate that this is disappearing. This is disappearing at this rate. So I have to multiply by -1 to get, you know, everything to line up in terms of units. So it's always a little tricky of an idea, so make sure you spend some time to think about it. Make sure it's making sense. Ask me questions if it's not. But these are the 3 types of rates, and it's the exact same experimental data. I want to be clear about that. It's just how we treat it that gives us these different options. And so this will always be the fastest rate. This will always have the sharpest slope. And then over time, that slope flattens out, and eventually the reaction will basically stop, and you just get like a flat line. We're not making any more C, we're not using up any more A, it might go all the way to 0. So the reaction rate is 0, because we have no more reactants to make products out of. And so we kind of approach that, with some curve. That's what's happening. So there's a maximum amount of C we're going to make. We're not going to jump straight to it immediately. It takes time to make it, but we get there. All right. And the less time it takes, the faster our rate is. The more time it takes, the slower our rate is. All right, so we are going to talk about the rate laws next. So we're going to spend a couple videos talking about how concentration changes rate, and then after that we'll talk about how time changes rate. But the whole reason that time changes rate is because our concentrations are changing, so our rate is slowing down. That's what happens. All right, that's the reason. But we'll talk about it more in the other video. All right, so next, rate laws.